I want to discuss now geosynchronous orbits. Geo is Earth, synchronous means at the same time. And so these satellites, they orbit Earth and they keep the same position relative to the Earth. So for example, if a satellite is right above me, as the Earth turns, the satellite will always be right above me. So if I'm here, the satellite will be here. It's always above the same point. As the Earth turns, when this position of Earth is this way, the satellite wants to be there. And so when the Earth when it's here, it wants to be here. So when the Earth goes 24 hours, the satellite comes back here. And so the question is, how high above Earth do they fly? How high, what should their radius be in order for them to maintain this? Well, the distance, let me call this here distance. It is r. It is r. And r is equal to the radius of the Earth plus their height. Radius of Earth plus the height of the satellite. I want to know the height. So if I figure r, I just subtract from it the radius of the Earth. That will give me the height. And then we can figure the speed too. So first of all, they spin around at a period of 24 hours, which we can change to seconds. I wrote it here. I have it as 86,400 seconds. So the period is 24 hours, which is 86,400 seconds. So the question is, where are they? Well, we know that it would be a circular orbit or some kind of an ellipse, nearly circular. So the force will equal to the mass times the acceleration. Since it's orbiting Earth, the force on it will be g times the mass of the Earth, mass of the satellite, divided by the separation between them squared. And this is the mass of the satellite, so it will cancel, times the acceleration. The acceleration will be v squared divided by r. V squared divided by r. And there is a relationship between v and r. V is 2 pi r over the period, right? Because it goes around. So it's 2 pi r over the period. So here I will have capital G, capital M divided by r squared. And v will be 2 pi r divided by the period, u squared. And don't forget about this little r here. So when you do this, you get capital G M over r squared equals to 4 pi squared. R squared over r just gives me an r, and then there is the period squared. And we want r. So multiply by r squared, you get r cubed here, and then multiply by t squared and divide by 4 pi. So you get capital G M t squared divided by the 4 pi squared will equal to the r cubed. And so you need to take the cubic root of this to figure out what r is. So r will be capital G, capital M, the period squared divided by the 4 pi squared, and we have to take the cubic root to raise it to the 1/3 power. So that will give me r. So let's calculate r. So G is 6.67 times 10 to the minus 11. M is the mass of the Earth, 5.98 times 10 to the 24th power. The period is 24 hours or 86,400 seconds. Plug that here and make sure you square it. Divide by 4 pi. Don't forget to square the pi. It's 4 pi squared. So 4 times pi times another pi on the bottom. So when you do that, let me see here. You get 4.225 times 10 to the 7 meters. 4.225 times 10 to the 7 meters. So that's r. So the height above Earth, right? This is r. We want to know the height above Earth. So you have to subtract the radius of the Earth. So that means h, the height, will be this minus the radius of the Earth, which is, again, 6.38 times 10 to the minus to the 7th. So you get about 3.59 times 10 to the 7 meters. 3.59 times 10 to the, I think 7 meters I said. I keep forgetting. Yeah, 3.59 times 10 to the 7. Which is about 22,300 miles. Approximately 22,300 miles. So the satellite has to hover above Earth at this height, at 22,300 miles, in order to be geosynchronous. The speed of the satellite, then you could calculate it. It's 2 pi r divided by the period, and we could calculate the speed of the geosynchronous satellite just by having, by the fact that it is geosynchronous, gives you the radius of it, and then it gives you the speed of it. The next question is, suppose I have a satellite orbiting at a certain orbit. And the question is, what is the kinetic energy of the object compared to the potential energy of the object? How much are they compared to each other? Let's see. Let's see if we can figure that out. Let me start here. Let me start in here. So I have this. Let me see. So let's say I have an object and is orbiting at some radius r. So I get the fact that, let me get v squared here. So I will divide by this. So I get v squared will equal to g capital M divided by r. And if I want the kinetic energy, I will multiply by half m on both sides. So I have 1/2 mv squared, and here I multiply by half m. So 1/2 g capital M. I'll put the m here, divided by r. So this is the kinetic energy. That's the kinetic energy of the object. What is this? Well, this sounds like the potential energy is g capital M, m over r. And so, but the potential energy has a minus sign, so it's negative 1/2 of the potential energy at that radius r. So the kinetic energy is equal to the negative of the 1/2 of the potential energy when you have an object orbiting around. And here is a question that might come in. And it says, for example, how much energy does it take to send a satellite from Earth? So initially it has kinetic energy equal to 0 to some orbit, and then it's, let's say it's a geosynchronous orbit. How much energy does it take it? Well, we can say the total energy at the beginning will equal to the kinetic energy at the beginning plus the potential energy at the beginning. But the kinetic energy, let's say the satellite is at 0, so it has 0 kinetic energy, so it is just the potential energy at the beginning. It's at the surface of the Earth, so the potential energy is negative g capital M, the mass of the satellite, divided by our Earth, right? It's remember, potential energy at any radius r is negative g capital M little m divided by r. The energy at the end, when it's finally orbiting, it's at a radius r. So the radius r, it has speed v. So it will be the kinetic energy at that orbit at the end plus the potential energy at the end. But remember, kinetic energy is negative half of the potential energy. And so I'm going to write here negative 1/2 of the potential energy. So the total energy will equal to, let me actually do it here. Yeah, I will stay here. So I get E will equal to negative 1/2 of U final plus U final. And so this is just 1/2 of U final. So the total energy will be 1/2 of U final. But U final is 1/2 of, U final is capital G, capital M, little m divided by R, but it has a minus sign. So the total energy is still negative. It's bound. It hasn't escaped. It only has a 0 potential energy at infinity. Okay, and so the energy at the end will be this. The energy at the end will equal to negative 1/2 of G capital M little m divided by R. Now, the final energy minus the initial energy is the energy you have to give it, the work that you have to do to increase the energy to this much. So the work done will be let's say it had 0 energy, 0 mechanical energy, and then it has, or let's say it had 10 joules of mechanical energy at the beginning, and then later it has 100 joules of mechanical energy, then the energy that was put in the system by doing work on it is the final minus the initial. So in this case, it would be 100 minus 10, and that's 90. So it would be E final minus E initial, and so that gives me this minus this. I'm sorry, this minus that. So it would be negative G capital M little m divided by R minus this one. But this is minus, so you put a plus, minus minus becomes a plus. G capital M little m divided by R earth. And so you get negative, actually let me factor the G capital M little m and then do this, 1 over R earth minus 1 over R. And you plug in the numbers. G capital M, the mass of the satellite, it depends. Right? So let's say you have a satellite of, let me go to my notes here. The book's example is 1,000 kilograms. Let's say the satellite is 1,000 kilograms. And so you get basically I forget, like you would get about 1,000 something. I'm sorry, not 1,000, like 10 to the 10 or something like that. So apparently I did a different example than the book. The book assumes it had an orbit already, so it had some potential and kinetic energy at the beginning, and then you raise the orbit to make it geosynchronous, and so it has a different orbit, and they did the calculation that way. I did the calculations just saying that the initial kinetic energy is 0, and we want to send this satellite to orbit. So it will be just whatever this is, the numbers there. I'm less curious about the numbers than the concepts. So I want to do one more example, and that would be it. It's about a binary star. So it's the final example in the chapter here. Let me write it down also. Here, example. Let's read it. The example says, astronomers discover a binary star system with a period of 90 days. A binary star system with a period of 90 days. Let me keep writing. And then it says, each star has twice the mass of the sun. So each star has twice the mass of the sun. Okay. And then it says here, how far apart are the two stars? Okay. How far apart are the two stars? Okay. And whenever we talk about these astronomical objects, we're ignoring, I mean, there are planets, every planet is pulling on the other, every star is pulling on the other, but we kind of ignore those as secondary effects. So for example, when we talked about the Earth orbiting the sun, well, there is the moon pulling on the Earth, and then there is Jupiter, and there are other planets pulling on the Earth and other stars, but they're far enough or maybe small enough that their effect is secondary, and the main effect is that of the sun. And so in here you have two stars, and they're here. So let's say here is star 1, and here is star 2, and they are a distance r apart. Let me ask you, where is their center of mass? Well, since they have equal masses, their center of mass is right here. That's their center of mass, is in the middle. And the center of mass, as these stars orbit each other, will not change. Because remember, how do you change the position of the center of mass? You have to apply an external force. And since I'm considering only a system consisting of these two stars, the force between the two stars is internal, and therefore there are no external forces. Again, there are other planets and stars pulling on them, but let's just ignore them. We just assume that the center of mass will be constant, will not change position. So the stars are going like this, and they finish their orbit in 90 days. And the question is, how far apart are they? All right, so, well, in fact, I'm going to call the distance between them as, let's call it capital D. And so each planet is going around this circle, a circle of radius r. And why does it go in a circle of radius r? This planet attracts this one, and this one attracts on this one. And so let's just consider one of them moving. And so we say that the net force on one object will equal to the mass of the object times its own acceleration. The force on it is g times the first mass times the second mass. Each of them has a mass m, so just m, divided by the separation between them squared. The separation between them is d, capital D. But that's twice the radius, so I'm going to just call it 2r squared. Actually, let me just call it d. Yeah, let me call it d. So the number we get will be d. So just the separation between them squared. Okay. Next, the mass times acceleration. The acceleration is v squared over r. So I have v squared divided by the radius, by r now, not by d. But r is d over 2. The radius is d over 2. Is d over 2. And so one of the masses goes away, so I have g m d squared here. The 2 goes upstairs, or actually let me just leave it there. So I get v squared, but so I have 1 over d over 2 right here. And then v squared, v is, since it's going around the circle of radius r in a period of 90 days, so that's 2 pi r divided by the period. So that's 2 pi r, remember, is d over 2 divided by the period, but remember to square everything. To square everything. So let's see what we get over here. I would get gm d squared over d squared is equal to 4 pi squared, and then d over 2 to the power 2 divided by the period squared divided by d over 2. Well, d over 2, this d over 2 cancels. And here I will have d over 2, so that's, and then there is a 4 pi here, so that becomes 2 pi squared. So I have g capital M over d squared will equal to 2 pi squared divided by the period times d. The over 2 cancelled with the 4 here. It became a 2. And I want d. So d cubed will equal to this. So I get d cubed will equal to, multiply both sides by d and solve. So you have d cubed will be g, oh, I forgot to square the period, t squared. Gmt squared divided by 2 pi squared. 2 pi squared. And so d will be capital Gmt squared divided by 2 pi squared to the 1/3 power. Now the hard part, joking, the easy part, is to plug in the numbers. G is 6.67 times 10 to the minus 11. The mass here, sorry, I switched from little m to capital M. The mass of each star is twice the mass of the sun. So you look up the mass of the sun and double it and plug it here. The period should be in seconds. So you have 90 days, change that to seconds. Make sure you square it. Divide by 2 pi squared and solve for D. I will quote you the answer. The mass of the sun, by the way, is twice the mass of the mass of the sun is 1.99 times 10 to the 30th. I just found it. And we have here So it turns out to be about 9.3. The separation between these two stars is 9.3 times 10 to the 10th. 9.3 times 10 to the 10th power. Let's see here. Meters. Okay. So again, this whole thing hinged on the fact that the center of mass doesn't move. We exploited that. And I just want to, let me see here. Let me make one more comment about the center of mass. When we talked about the Earth orbiting the Sun, so here is the Sun, here is Earth, we said it goes like this. Now what's wrong with this? Because it says the Earth could be here, the Earth is here, the Earth is here, the Earth is here. This is not completely accurate. The reason is, the center of mass, well, the Sun is much, much heavier than Earth, that the center of mass is not even here. It's actually within the Sun itself. So let's say, in general, if the center of mass were here, when the Earth is here, the Sun has to move a little bit here so that the center of mass will remain at the same place. So that's what I wanted to say. The Sun would be here when the Earth is here, when it's here. And when the Earth is here, the Sun would be somewhere here. It has to change position in order for the center of mass to remain. But in the case of the Earth Sun, again, the center of mass is within the Sun. You can calculate that. And then yeah, let me see if I can look up the numbers. Let me just show you that the center of mass of the Sun is within the Sun. I found the numbers here. Let's see. The radius of the Sun, the mass of the Sun, the mass of the Earth, and then the distance from the Earth to the Sun. Let's write all of them down. So the mass of the Sun is about 2 times 10 to the 30th, 1.99 times 10 to the 30th, 1.99 times 10 to the 30th kilograms. The mass of the, I'm sorry, this is the mass of the Sun. The radius of the Sun is 6.96 times 10 to the 8th. 6.96 times 10 to the 8th power meters. The mass of the Earth, 5.98 times 10 to the 24. You see, this is much more massive, about like a million times. And then the distance from the Sun to the Earth is 1.5 times 10 to the 11th. 1.5 times 10 to the 11th. 1.5 times 10 to the 11th meters. Okay. So let's see. So here is the Sun. Let's just draw this picture. Here is the Earth. Sun. Here is Earth. Let's find the radius of, the center of mass. Here's the x-axis. This is x equal to 0, and this is x equal to 1.5 times 10 to the 11th. So the position of the center of mass will be, remember, m1 x1 plus m2 x2 divided by m1 plus m2. m1 x1, the mass of the Sun times the position of the Sun. Both are, the position of the Sun is at 0, so this is 0. This is the mass of the Earth times the distance from Earth to the Sun, the position of Earth. So mass of the Earth is 5.98 times 10 to the 24 times 1.5 times 10 to the 11th, the distance. And then here, the mass of the Sun plus the mass of the Earth. The mass of the Earth is much, much less than the mass of the Sun, so it's basically the mass of the Sun, basically 2 times 10 to the 30th. Because you're adding this plus like 1 part in a million, so it's approximately the mass of the Sun. I would write it as 2 times 10 to the 30th. And let's see what we get here. Where is my calculator? So I get 5.98 times 10 to the 24th power, and times 1.5 times 10 to the 11th power. See, we're dealing with very large numbers. That's why people use the phrase astronomical. Everything is large. and then times 10 to the, divided by this thing times 10 to the 30th. So that happens to be 4.5 times 10 to the 5th. 4.5 times 10 to the 5th meters x center of mass. Look at this. The position of the center of mass from the center of the sun is less than the radius of the sun. So the center of mass is actually within the sun itself, and it's deeply within. The radius of the sun is like 10 to the 8th, so it's like 1,000 times more within. Okay, I will stop here, and I will see you back when we do the problem solving for this chapter.